Hello, my name is Joshua Lewis. I'm a senior here at the Colorado School of Mines working for Dr. Lincoln Carr, and soon to be graduate student in the quantum engineering program. I would like to thank everyone who is taking the time to see my presentation today. And on that note, let's get into it. I would like to begin by discussing the scope of fractional calculus, and then I will describe the relevant mathematics. Now, why is fractional calculus important in physics? Experimental evidence suggests that transport within porous materials, clusters of neurons, disordered media, and multi-scale systems are not accurately modeled by classical Brownian motion according to Fick's laws. These vastly different systems share distinct emergent phenomena, such as long-range correlations, non-locality in either space or time, fractional geometry, non-Gaussian statistics, and non-Fickian transport. These many types of fractionality can be exploited to develop a fractional differential equation that more accurately models these different emergent phenomena. This allows one to not only describe the properties of an existing multi-scale physical system, but also allows one to design and build advanced synthetic materials with prescribed physical properties, such as enhanced mass exchange and charge transfer rate to particular regions. Of particular interest in our research group is the relation to quantum information processing with highly connected systems. It has been shown that complex networks and complexity science can be related to the same source of space and time non-locality as found in the fractional Schrödinger equation. Our focus is mainly on those systems that show long-range correlations and non-locality in either space or time. Hence, we are most focused on two specific fractional operators, one that displays spatial non-locality and one that displays our temporal non-locality faithfully. We will first delve into what it means to have non-locality in space or time. The case for the spatial non-locality is somewhat intuitive. Unlike in an integer representation of a simple physical system, where the evolution of a system is dependent entirely on what the value of fields are at a local neighborhood, spatial non-locality implies that evolution is dependent not only on the fields in a local neighborhood, but also on a larger neighborhood that may take the entire domain. To give an example, we imagine a simple one-dimensional hopping chain, where the Hamiltonian is not defined using only nearest neighbor interactions, but also defined with non-zero interactions with neighbors along the entire chain. Temporal non-locality can be understood in a similar way. A more intuitive term for temporal non-locality would be that of a memory effect. A system with memory effects appears to have a memory of what happened prior, and this memory impacts the system as a whole. Examples of such can be found in some complex networks, such as a memristor network. It is important to understand that our fractional operators must reflect these slightly different properties in how they operate on a spatial or temporal variable. Let us go ahead and define these operators with this in mind. The heart of fractional calculus surrounds the following question. Is there such a linear operator such that when applied an integer number alpha times yields the first order derivative? This simple question leads to the basic construction of many different operators that fulfill this requirement. The operators we'll be focusing on today will be the Ritz derivative and the Caputo derivative. We will now briefly understand the source of these operators. Using the Cauchy equation for repeated integration, we find that the nth integral may be written using a single integral, as seen above here. Adapting this to a fractional order is as simple as allowing n to take non-integer values. It may be further shown that this integral successfully has the semigroup property as well. As such, successive applications of the operator yields an integer order integral in such a way as we desired. Because the semigroup property is valid, we may then apply an integer order derivative to recover a fractional derivative from the fractional integral definition. Doing such defines one of our vital fractional operators, the Caputo fractional derivative. Here we have the definition of the Caputo fractional derivative of alphath order. It is important to note that the derivative specified here has bounds, and we have the additional freedom on defining a left-handed and a right-handed operator. The operator defined above is the right-handed Caputo fractional derivative. However, to obtain the left-handed derivative, we just need to simply exchange the bounds of integration and negate the x minus t term in the integrand. If we look at this operator in depth, we can see that unlike the derivative, where the value is defined for a single point, here the fractional derivative is most definitely non-local, and that it requires information from a subset of the domain to determine its value at a single point. The Caputo derivative either requires information from the left of the examined point or from the right. For time, this may be interpreted as the Caputo derivative requires information either from just the past or just the future to determine motion. The Caputo derivative in this way is not symmetric, and thus we must define another operator that allows us to work with symmetric derivatives. This is just a combination of both the left-handed and right-handed Caputo fractional derivative. We call this derivative the Rietz derivative. This derivative is vital in the faithful reproduction of the second derivative in physics due to its symmetric nature. With all this understanding in mind, we define the one-dimensional fractional Schrödinger equation. Here we have the integer order Schrödinger equation. Let's look at the fractional Schrödinger equation one step at a time. We may start with the left-handed side and derive what the time-like portion should look like. We know that we desire a fractional operator to replace the partial time derivative, which only requires time from the past. Thus, we use the left-handed Caputo derivative. We may then define the spatial portion by replacing the second-order derivative with the Rietz derivative of order 2 alpha. We then add a component to account for an arbitrary potential, and we have the fractional Schrödinger equation. The important point to note is that when delta and alpha are equal to 1, we recover the classical Schrödinger equation. Now, finding tractable analytic solutions to the fractional Schrödinger equation is in general far more difficult than that of the integer order version. Due to this, numeric methods of simulation are vital. Our research has produced new novel methods for numerically solving such an equation with a greater speed and efficiency at the cost of long-term stability than that of the general finite difference method used to solve the fractional diffusion equation. Two methods are used in conjunction to solve this fractional differential equation. First, a truncated series is developed to define the Rietz derivative in terms of integer order derivatives. And then we treat the Caputo derivative as a Volterra integral equation of second kind, as many have done in solving the fractional diffusion equation numerically. Using both of these methods in conjunction in this way allows us to parallelize our numerical simulation in a much more efficient way than that of the finite difference method. Let us first examine the steps used to solve the spatial-like portion of the fractional Schrödinger equation. First of all, through the course of our research, it was discovered that the fractional operator closely related to that of the Caputo fractional derivative may be written in terms of an infinite series of integer order derivatives. Using this in its relation to that of the Caputo fractional derivative, we may rewrite our spatial component of the fractional Schrödinger equation as a truncated series of integer order derivatives. Here we have the truncation error collected from attempting this with two functions of hyperbolic secant and hyperbolic tangent. We may notice that given between 3 and 5 terms in the series, that we obtain the answer with a truncation error less than the magnitude of 10 to the negative 1. This allows us to at least transform the spatial portion into an integer order differential equation. After this, a fourth order Runge-Kutta method was used to further obtain the solution to the spatial portion of the fractional Schrödinger equation. Now, if we consider the fractional Schrödinger equation in a classical infinite potential well with a width of 2a, where only the spatial component is fractional, we obtain the following wave functions that solve this equation. Here we have the following stationary states of the fractional Schrödinger equation with no time fractionality. We notice clearly that with an order less than 1, there is a sort of bunching in the middle that we can relate to that of subdiffusive transport. We may then also note that with an order greater than 1, the wave function has a greater amplitude near the boundaries of the system. This can be related to that of super-diffusive transport. Here we may see some higher energy solutions to the fractional Schrödinger equation that accentuate these properties. Now, when allowed to evolve through time, it was discovered that the evolution of a state is quite similar to that of the integer order Schrödinger equation. Each state may be decomposed in terms of the fractional stationary states, and each state acquires a complex exponential phase where the exponent is proportional to the eigenvalue of the spatial portion of the fractional Schrödinger equation. Using the standard definition of the inner product and under the assumption that the definition for the probability density is the same, we find that probability is conserved. However, when the temporal portion of the fractional Schrödinger equation is allowed to take on different orders than one, the evolution is much more complicated, and using prior definitions, probability is no longer conserved. This hints at the fact that either a slightly different operator should be used to evolve in time, or that assumptions made in defining the inner product and probability density are incorrect. Our future work is to develop more rigorous conservation laws that allow us to arbitrarily adjust orders. This amounts to generalizing Noether's theorem. We would also like to define physical quantities with importance to the system, such as an analog to velocity or momentum. Finally, with a future goal of adapting to the many-body case, we would like to investigate the second quantization with respect to fractional quantum mechanics. And that is the end of my presentation. Thank you all for attending and listening.